we're going to go ahead and get started. Um, so we've reached the final session um, today. This will be talking about models. Real quick, if you guys are not familiar with me, I'm Harpreet Sahot. I'm a hacker in residence at Voxel 51. Been here for about a year and a half. I've been doing deep learning for a few years at this point. I worked at a number of different companies. My background's over the last, how long ago was it that I graduated grad school at this point? I can't even remember when I graduated. So I think 2013 is when I graduated. Yeah. So over the last 12 years, just math and coding. It's pretty much what I've been doing. Uh, this agenda is false because I forgot to update it. So ignore the agenda. But the rest of this information is not false. So just a quick recap over the last couple sessions. You scan these QR codes. It'll take you to the YouTube videos. Session one was just a overview, I say overview, but really it was in depth. There's an accompanying GitHub repo and all that stuff for it. All the links, you'll get all the links, guys. But we just talked about the research landscape, the history of it, to talk about the current capabilities, limitations, and then kind of opportunities for, things that you can potentially do. The session two, which was a previous session, talked about how to create GUI datasets. So it's all about datasets, is what that session was all about. Through that session, I hope to impart a appreciation for what it takes to create a curated GUI dataset and hopefully have a repeatable methodology for building training data. The point I want to drive home during that session was just the importance of data quality. This session, we're going to talk about models primarily. So I'll talk about some fine-tuning strategies. I'll talk about some architectures out there, and I'll talk about the challenges I faced this week. I spent many long hours. Like I had so much more planned for this session, but the thing that took a lot of my time and all my time and kept me up until about 4 a.m. yesterday was just getting the fine-tuning script ready. So what I'm going to present to you today is like I couldn't find any tutorials on how to do this. So I kind of had to create it from scratch. There's a lot of pain that I felt along the way, a lot of headaches, a lot of late nights, and hopefully I can impart some lessons upon you. It's going to be anticlimactic in the sense that, the model that I created, the training skip works. The model does, in fact, train. I just didn't get a chance to implement it as a remote source zoo model, so we can't actually see the actual output. But what's going to happen is, you guys have to GitHub repo. I'm going to update that through today and Monday. So by the time you see it Tuesday morning, let's say, it'll have or Tuesday evening, it'll have, it'll be complete, right? But that doesn't mean there's not a lot to learn today. So let's get to it. So we're going to talk about models. We're going to go in depth talking about models. I'm going to talk about a few models that I've hacked around with and that I've implemented as a remote source zoo model in 51. And then what I'm going to do is I'm going to talk at a high level about the architecture of these models. And I want you to pick up on a theme. What do you see as a theme of these models? And then we'll discuss that in a little bit of detail there. So first model I want to talk about is called OS Atlas. So this model, I like it a lot. When I initially implemented it and hacked around with this model, integrated as a remote source zoo model in 51, so you can easily run it across your data set. I like that it was very robust in the sense of its capabilities for UI element localization, and it was actually very invariant to prompt. And one thing that I'll talk about later is my pain with prompting these models. There's also really good semantic understanding of user intent, and it was really good at like kind of single target detection. So it was a really good model. There's two flavors of this model. There's the base model, and then there's the pro model. I found, at least in the couple of days I spent hacking around with this model, that the pro model follows instructions better. Sorry, the base model follows instructions better than the pro model. Some things that I noticed was a little bit of inconsistent output formats, but with some decent regex parsing, you can get the output uh, coalesced in such a way that we can nicely visualize it in 51. Um, this model in particular, let's talk a little bit more in detail about it. So, of course, it's a GUI action model. And essentially this, like all the models and like everything we've been talking about throughout the series, like it's trying to understand and interact with the graphical user interface. And so this model was focused on, how well could this particular model perform in like unseen out of distribution scenarios. And here they had a two-phase training process. So the first was actually a GUI grounding pre-training. So here they're teaching the model to understand a GUI screenshot, then identify the elements on the screen. And so it's trying to teach the model to accurately locate and recognize GUI components. And of course, the key component here is data. So they had a massive, diverse, multi-platform GUI grounding corpus, the largest open source corpus to date. And this had over 2.3 million unique screenshots and more than 13 million GUI elements. So it takes a huge amount of data to even go from a base vision language model to fine tune it to be a GUI model. And so, of course, that's one phase, right? The GUI grounding pre-training. Then there's the action fine tuning. So the action fine tuning stage, what they did here was trying to transform instructions to executable GUI actions. And so they had introduced a unified action space, as we see here. And so it's attempted to standardize semantically equivalent actions across different platforms, right? And we talked about this in the previous session, right? Tap on a mobile, click on a desktop, like they mean the same thing semantically, but we call them different things. But in this case, they unified it and just called it, a click action. So this is nice because we're reducing the number of unique action types from, seen in previous data sets from 17 to now just 10. Right, and it resolves conflicts like tap versus click, press home versus home, type versus input, so on and so forth. And the model they use here actually is Qwen2VL, right? This is the primary backbone model they used. And interestingly, what they did here was actually preserved the complete Qwen2VL7B instruct architecture, right? They didn't really change the architecture at all, but what they did was this specialized data and training methodology. So they didn't modify the architecture, they focused on the data and built this model from that. And this is, Qwen2 itself, right? It can handle an arbitrary image resolution, which, as we know, is essential for GUI screenshots. We talked about in the last session how GUI screenshots are just really, really high resolution images, more so than natural images, and the complexities that come with dealing with this type of image resolution. And turned out Qwen2 can handle any arbitrary resolution. And so from there, we're able to then map this dynamically to a dynamic number of visual tokens. And here we had, in this case, they had rather images that were up to 1024 by 1024 pixels. Then they also focused on really consistent data formatting and introducing special tokens or using the special tokens from Qwen2VL and having a very consistent format for the bounding boxes. And so it took Qwen2VL without altering its core architecture. It was able to specialize it for GUI tasks through just extensive targeted pre-training and coming up with a unified action space and just focusing on data. And no real architectural changes here. And they're able to come up with a very strong model. The next model I want to talk about is MemoVL. So this is a model that came out, I think, just in May of this year, if I'm not sure. This model defaults to outputting bounding boxes, but I was able to, prompt engineer my way to getting this to output key points and actually output structured JSON, which is useful for downstream integrations. In this case, the downstream integration was integrating into 51 so that we can add them as detections or key point fields on a data set. OCR in this particular model, like all models on GUI screenshots, right? GUI have a ton of text. The text is varying resolutions. And there's, of course, different font sizes, different headings, things like that. OCR is hard on GUIs, essentially. So, of course, like there's a slowdown here in terms of how long it took to perform the GUI grounding. Read the text GUI, where it's just like essentially printing off the text from a GUI relatively fast, but sometimes you're more interested in grounding text, like can it locate particular text on the screen. This model also showed some really good UI navigation capabilities. So I found it to excel at just understanding the different elements on a interface, and then from there being able to generate some coherent multi-step interaction sequences, which of course, it's valuable for UI automation tasks. Also, this is interesting because this model, as you'll see when I hover over some of the detections here or key points here, some of them actually have thinking tokens. So this is a reasoning model. So it gives kind of more insight into the model decision making. Of course, prompt engineering, getting this model to output structured JSON and do what I wanted it to do. Your mileage might vary. My implementation of this model as a 51 remote zoo model, I play around the prompts a lot, and I feel like the prompts I got are pretty strong and do a good job. And so, of course, at the end of this session, you'll get a QR code to this very slide deck that I'm working on, that I'm presenting to you. And in this slide deck, if you look at the presenter notes, you'll have links to all these models and the Getting Started notebook, so you can play around with them as well. But let's talk about this architecture for this model, right? So this kind of has a hybrid design which has three components. So there's the vision transformer, which is kind of the eyes of the model. In this case, they used Qwen 2.5's vision encoder. And so the vision encoder, this is going to process the visual inputs like the image. And this is cool because it'll handle the native resolution of the input so that we're able to preserve those fine-grained visual details. There's also the MLP projector that we see here. This is kind of like a translator. So it maps the visual tokens from the vision encoder into a latent space that the language model can understand, right? So if you've worked with vision language models, you're familiar with this. That's kind of, a standard operating procedure. And then they have the MIMO 7B language model. So this is initialized with the MIMO 7B base language model, and this is responsible for text understanding. So this model, it has eyes in the sense of it has the vision transformer, and it has the brains and the translator, in the sense of the MLP projector and then the language model. And so this is trained using a two-phase approach, right? So each phase has some different components to it, right? The phase one training of this was just warming up the projector. So kind of having that MLP learn to connect visual data to some language representation. There's the alignment with the vision encoder. So in this case, the vision encoder was unfrozen, and then it was trained with interleaved image text data. So that it's able to strengthen its connection between the language model and the vision encoder. Then they had this kind of general multimodal pre-training. So all parts of the model were trained together on a huge range of data. This is OCR, grounding, video, GUI data. And then they had a long context supervised fine-tuning stage. And so this was focusing on extending the model's ability to handle longer inputs and produce more complex reasoning tokens. Then they had phase two, right? So once phase one was complete, phase two was using some reinforcement learning. So they talk about something called mixed on policy reinforcement learning. And so it's a post-training phase, of course. And they combined some elements of RL here. I'm by no means an RL expert, but they used reinforcement learning with verifiable rewards. So this is essentially just like a rules-based reward function. And then there's reinforcement learning from human feedback, right? And of course, the touched on this, the Quinn 2.5 VL was the backbone for the vision encoder, right? And again, this is nice because it's supporting native resolution inputs. So we're capitalizing on Quinn 2.5 VL's ability to process these high resolution images. It's not a direct fine tune of Qwen 2.5 VL because they switched the LLM backbone. They used the MIMO 7B backbone, which has different configurations than the LLM backbone of Qwen 2.5, but the vision encoder they took from Qwen 2.5 because, again, it's able to handle arbitrary image resolution sizes. There's a question that came into the chat here. Are interface design systems leveraged when available in any way to train these GUI models to learn to identify elements? Yes. So that was what the previous session was all about. So I do recommend watching session 2. So because we talked all about that in great depth. So definitely check that out. I think you find your answers there. The next model I want to talk about is called Show UI 2B. So this model, of course, a 2B parameter model, great, 2 billion parameters. I like it. I can run it on my consumer GPU. Even up to 7B, it's nice. I could use it on consumer GPU, but it's really nice to get it down to 2B. So this is quite nice because we can get dual output formats. We can get simple coordinates, or you can prompt it to give you a structured output. And it's actually pretty fast, of course, being 2 billion parameters compared to 7 billion parameters that we've seen in other models. It's pretty fast. And that's considering the fact that I had like pretty massive system prompts. The one thing I didn't know, a few things I didn't like. One of them was the fact that I couldn't get this model to accurately identify what type of environment it was in, right? So it couldn't accurately tell me whether it was in a website or a application or a desktop OS environment or a mobile OS environment, right? It struggled with OCR because we have high resolution images. Some text is quite small. So this struggled with that more so than the other models. And you'll see some of the points that we have, right? Like you see the points are kind of a bit off in this GIF I'm showing you here. It points around kind of the general area of where it should point, but not exactly at it. So that was a interesting thing to note. It's funny because you can completely miss the mark, but you're in the bounding box, so you still get counted as right. So that's you can kind of inflate your performance in that way. Just kind of an odd thing I noticed is trying to get it to work with calendars that are on kind of a GUI. That's basically useless kind of for fine-grained text targets. Yeah, so it's good, decent model, right? I mean, there were some redeeming qualities. Core grounding capabilities were decent. It was fast. And this case, they just released actually recently, I've yet to integrate it yet into 51, was the Show UI that's built on Qwen 2.5 VL. In this case, this is built on Qwen 2 VL, the one that I'm showing here. Either way, like it's an imperfect model, but it's small and you can fine tune it to do better, right? So it's a good place to start for something very specialized. Talking just a bit about its architecture. So this is built on Qwen 2 VL 2B. And so the challenge here, of course, with all of these tasks is the fact that we have high resolution UI screenshots, right? When we have high resolution UI screenshots, we end up with very, very lengthy visual token sequences. And this leads to bottlenecks, computational bottlenecks. And then also, like a GUI has a lot of redundant empty space, right? Simple backgrounds. and just redundant empty space where there's not a lot of visual interest. Um, but then like the stuff that's really important tends to be small, right? So the critical elements tend to be small. So that's a challenge. So what did these guys do? They created something called a UI connected graph. And so they represent each patch as a node, and they link neighboring patches with the identical RGB values. And so it's kind of adaptively guiding token selection. And so during training, what it does is it's randomly going to skip a portion of the redundant tokens within each component and then leaves out single patch components. And then it kind of just retains the original position embeddings for that selected token, which is important, of course, for UI element grounding. So by kind of using this interesting graph design, they reduce redundant visual tokens by a third during training. And then, of course, if you're able to reduce the number of tokens, you're speeding up performance. They also have, as you see here, a interleaved vision language action streaming kind of module here. So of course, as we know, GUIs have really complex multi-step trajectories, right? And the action space varies across devices, across operating systems, and things like that. So what they did was they had their action space in a standardized JSON format, and then the model is given a README in the system prompt that details the action usage, and it encourages the model to kind of interpret rather than memorize. So their system prompt is it tells the model what actions it has available to it, which is pretty interesting. But the implication of that is when you try to change the system prompt and have the model do something else in a different kind of action space, it tends to fall apart. A key component, of course, again, is the data. Really, they had small scale but high quality GUI instruction following data sets. So really good data set. It's small scale, but it's still like orders of magnitude larger than what it is that we created last week, or what I showed you last week. The next model I want to talk about here is called GUI Actor. So this is my favorite model, and also the model that I ended up choosing to fine tune. Why do I like this model? Well, just the consistency of its output format. So it gives you really predictable key points and attention maps every time. And this is irrespective of how you prompt it, right? It's really robust, prompt invariant, I would say, in a sense. And like it just does a good job, and you get that built-in explainability. So I like it a lot, right? So we have this kind of attention heat map that we get, which kind of makes it easier to debug the model behavior. This model comes in a couple different sizes. There's a 7B parameter model and a 3B parameter model. In the fine-tuning script that I'm going to walk through and talk about in a little bit, I focus just on the 3 billion parameter model. So let's talk a little bit about this model's architecture. So this model, its primary kind of focus is to solve visual grounding for GUI agents, right? Visual grounding, like it's a very, very core like challenge. It's a hard thing to do. So we can't really get true agency of a GUI agent unless it's able to do visual grounding. So it's like kind of table stakes, and a lot of models don't do it that well. So this is really good starting point, and kind of really what the focus is of what we ended up building for our data set, and what we ended up fine tuning is just GUI grounding. But of course, it helps this visual agent pinpoint exactly where to interact based on the visual input and the natural language instruction, right? So this is the core of GUI grounding. And so sometimes, traditionally we'll get coordinates like as text, x equals some point and y equals some point. So this has some limitations because we end up with a very weak connection between the visual features and the numeric coordinates. We also end up with very ambiguous single point predictions for a clickable area, because fundamentally there's a mismatch between the vision model patches and then this pixel level kind of precision. So what they try to do in this model is actually just mimic humans, right? when a human interacts with the GUI, we're not calculating a coordinate. We're just perceiving and interacting with the element. So what this model did was they used Quinn 2.5. It's built on Quinn 2.5. And then they add some specific components for GUI grounding. They talk about this actor token, which like they talk about the actor token, but like when I look at the model config, the special tokens map, the vocab, like I don't see the actor token anywhere. So I'm scratching my head, like where is that actor token? And even in like the GitHub issues, they talk about the actor token. And I'm like, where is this actor token? Maybe it's somewhere implicit in the model. I'm not sure, but I just yeah, I spent a lot of cycles, brain cycles, more than I should have, trying to figure out where the hell that actor token was because I needed to try to build it into my prompt. But anyways, there's an actor token, which I'm assuming is implicit based on the other tokens that are mapped, the other special tokens. That's helps you encode the intent of your action by combining the instruction and the screenshot context. And they have here a attention-based action head. So instead of generating coordinates, it's using attention to directly point at a relevant screen region. So the visual patches are going to go through some type of self-attention to understand the GUI context. The model is going to compute attention scores between the human's intent and the visual patches. Then we create a heat map that shows kind of the importance of each screen region. And they do this through multi-patch supervision, right? So we're training on entire clickable areas rather than single points, which matches how humans interact. And as part of their process, they use a grounding verifier as well, which is just a lightweight second pass system that kind of refines decisions when there are multiple possible regions that we can click and selects the most appropriate target. But here they're using Quinn 2.5 VL's general knowledge, and they actually end up only adding 100 million parameters with their modules that they add. So it gives it teaches that base model a direct visual way to understand where to click. So we go from kind of more of an abstract, point to just a more intuitive kind of attention-based interaction. And when we kind of see that here, in the output, right? Right. So it's quite good at that. All right. So maybe you picked up on a thread here, the importance of Quinn VL, right? So Quinn 2 VL, Quinn 2.5 VL has been huge for GUI agents in the last year or so. And I think there's a clear kind of before and after in performance capabilities because the native model is so good. Like Quinn, just the native model itself does really well on benchmarks. And part of the reason that I think the community has adopted it is because it supports arbitrary image resolutions. It has some really unique, interesting kind of embedding techniques. And it's open source, right? So, of course, it's fully open source, Apache 2.0. I believe it's Apache 2.0. And so this democratizes research, right? And it gives the ability for people to hack around and play with stuff. And yeah, it's been huge for this area of research. Of course, there are some pain points that I've felt with all the models I just discussed. One of them is the output standardization. I mean, much like with the GUI datasets, there's kind of this chaos, if you will, for how models output stuff. Every model is kind of reinventing how to output coordinates, tuples, JSONs, arrays, whatever. Prompt engineering seems to be very, very difficult. I've seen models break by just adding a white space. I've seen models break when you kind of stray from the system prompt, right? Which I feel like they shouldn't do. So there's some pain that I feel working with these models. So one thing I wish was that there's more kind of built-in explainability, right? So GUI actor kind of has those attention heat maps, which we saw are nice. Mimo VL, it's nice that it gives us thinking tokens. I was reading through GUI actors issues, and apparently the next model they're going to release will be a reasoning model, so it'll have thinking tokens. So excited to have that come out. But yeah, I mean, every model that I've talked about so far seems to struggle with small text and OCR, and you know, grounding can be better. Question here: does GUI actor support high and low res with high accuracy if we don't have control over resolution? Which model is best suited? So, I mean, any model that's based on Qwen 2 or Qwen 2.5 VL is probably going to be the way to go, because, as we mentioned, those vision encoders are able to support an arbitrary resolution. So, I think that's going to be the bet. So some things that I'd like to see in some future work is just models that are more multilingual in output formats. You saw in last week's session that I showed you that plugin that I built for 51 that does synthetic generation of data. That I built. One of the modules was just using Qwen 3 to translate the instruction to a different language, right? So that's one way we can augment our training data. I feel like we're spending a lot of time coding, just handling the different format variations. I think the energy that we put into that could be better spent somewhere else. And maybe that comes down to a kind of universal language for UI interaction, or maybe one schema that is able to understand a tap and a click are the same intent, but just a different kind of context. I feel like prompts are a little bit too brittle. More so than just a standard language model, right? I feel like if I take Qwen 2.5, just the base language model, and I add white spaces and whatnot, it doesn't impact the output too much, whereas it can completely break for this GUI interaction type of use case. Now, that being said, I'm going to talk about how to format GUI actor to our domain. But before we do that, I'm going to share these notebooks with you. Of course, you'll get the links to them. I'll be sure to have the links to all these. But this notebook, it's still running, taking a bit long here. So unfortunately, can't explore the results. But what I'm gonna do is I'm gonna share it here as a link, and you guys can explore it a little bit later on your own. But what this is going to do is it's going to, I created a kind of grounding evaluation data set. And, if you recall, like it's a ton, like, the amount of effort and work that it takes to create a grounding data set or any data set, really, it's just a ton of work. So, this isn't a true benchmark in any sense. And this, I basically what I did was I just took the training data that I had. I used 51 to create patches of just the boxes. And then I used the plugin that I had to generate synthetic task descriptions. So definitely not the most, not even remotely close to the correct way of creating a benchmark data set, but it's just what I could do with the time I had available to me. So that being said, it's what we're working with. So that's the data set you're going to download, and then you'll see here how to use GUI actor in 51. So I've implemented this as a remote source zoo model. So if you go to my GitHub, and you go to the repositories that I've created, you'll see that I've done a lot of stuff here. All the logic is kind of baked into here. So let's just do a couple of things here. I just want to pull out, for example, here's like OS Atlas, or here's UI tars, or Mimo VL, show UI, Kimi VL, right? So I'll drop all these links here in the chat. And you can hack around with these models because every one of them has like a notebook that will show you exactly how to get started. And what I recommend you do is just replace this data set with the one that I created. And of course, I have to change the prompt field to be something different. In this case, the label field will be just task. But definitely check that out. So there's OS Atlas you guys got. UITARS, this gave you the link for. Mimo VL is right here. Show UI is right here. And Kimi VL is right here. And as you explore these integrations, look at the zoo.py file, and you can see how I'm prompting the model to give me output. Right. So you'll see all the different system prompts I set up, and then kind of all the logic it takes to get the model to run and work with your 51 data set and parse the outputs correctly. But for you, the end user, it's just a simple pattern of registering the zoo model, loading the zoo model, and then using this apply model. So real friendly interface for you to just hack around and get started with these models. So that'll be your homework for today, is take the data set that is here and play around with these other models and see how well you're able to do. Right. So before we get started on this, you'll notice that the training data set that part of your homework was to make that training data set more robust by generating synthetic samples. So there's the train data set, because it took me a very long time to generate just 739 samples, right? And so it's painstaking work, hard work. But of course, we built this plugin that I showcased to you last week, which was the plugin for creating synthetic data in 51. So dropping the link here for the synthetic data plugin. And what you could do is then actually create a ton more synthetic data using this plugin via the SDK, right? So what this is going to do is it'll download the grounding data set, the one I just showed you right here. We'll load this data set, and then we'll start running the different operators for this model to run the synthetic generation pipeline, right? So this will just rephrase all the task descriptions and what's happening at each iteration, right? We start with 739. We run this, we'll end up with nearly 1,500. We'll run this, we'll end up with nearly 3,000, nearly 6,000, 9,000, right? So on and so forth. So by the end of this, you'll end up with a data set that is very, very large. So starting from 739 samples, you'll end up with somewhere around 30 to 40,000 samples. Push it to the Hugging Face Hub and then fine tune on that. This is kind of indiscriminately creating synthetic synthetic samples in your data set. Last week's session, we talked about how to be more smart about creating samples, kind of explore your data a little bit more and then create samples that way. But if you're in a bind and you just need to create variations of a data set of some samples, this is going to be the way to go. So by the end of this, you'll end up with well over 30,000 samples that you can then fine tune GUI actor for. So before I jump into the code that I wanted to share with you and talk about specifics of the code, I just want to talk about what I had to do to get to this point, right? So what did I have to do to customize GUI actor to work on our specific data set and our domain, right? And we'll look at the code and we'll step through the code in more detail, but talking at a high level, the first thing is formatting a data set. So there's a huge challenge when we're trying to adopt the 51 annotations for the GUI actor model. As we've seen, 51 is storing the UI interactions as key points and bounding boxes that are attached to a sample. But when we're training our model, we need a JSON-like structure that's a conversation, right? So as you'll see in the code that I'll show you, I created just a quick function that transforms and converts 51, or really just constructs the message on the 51 sample, right? So again, I'll show you in a second, but each annotation, we extract the task description, element information, action label, and the different coordinates, and then structure this as a three message conversation with the system prompt, user query with the image, and then the assistant response with the ground truth. And so there's some challenges with respect to maintaining the different coordinate precision through the transformation. And so, there's just a explicit format conversion from 51's kind of width height representation to what GUI actor expects, which is min-max coordinate system. So just a couple lines of code. And then what I did was when we created the data set initially, we had one sample with multiple annotations, right? And if you take that one sample with multiple annotations and you run it on a single GPU setup, you're going to run out of GPU RAM like very, very quickly. So what I had to do was flatten the data set, right? So ended up with that one screenshot and its many annotation to then just samples that point to the one screenshot and then have just that one annotation as part of the conversation. I'll show you that in a second. So this way we just have screenshot, one annotation, rather than screenshot and like up to 200 annotations, right? So it just makes it nicer for those of us who are GPU poor. Next was then collating the data set. So once we construct the messages in the way that the model expects, the biggest challenge was collating the data set. Because I'm going from something kind of different than what the original model was trained from, and trying to coalesce it into what that model expects. And so this was a bit of a challenge for me. So I had to, the most challenging aspect, I think, was just connecting the text instructions to precise locations and tokens for the model to handle. So I extracted the ground truth coordinates from the annotations, and then it did a two-step kind of transformation. So I replaced the text-based coordinate references with what the model expects, which are special pointer tokens that were placeholders in the instruction text. And then I normalized coordinates to the specific visual token indices. So then it kind of corresponds to how the vision encoder is going to process the image in patches. So GUI actor does point interactions and box interactions. And so for point interactions, I just calculated a specific visual token that contains the target coordinate. And then for the region selection, I implemented kind of a more complex, it was in the original code base. I just had to do a little bit of hackery with it, but just created a binary mask that identifies all the visual tokens that overlap with the target bounding box. And so this helps the model now handle both points and bounding boxes, because that's what I had in my data set. And so, yeah, there's some, trying to build in that spatial alignment, essentially, right? We wanted to build in spatial alignment between the text instruction and the image region. And so it was just what we had to do during the collation process. And the one thing I had to do was I had to use the image, when you run a model through when you run your conversation payload through the processor for the model, you end up with a dictionary, and the dictionary has like pixel values and text, embedding values, all this stuff, right? What I did was I used a key from that, which was the image grid THW from the processor, so that way the token mapping is aligning with the vision encoder's kind of internal representation. Because otherwise I'd end up with just tokens that are out of it. It was just a headache. It was a headache. But anyways, by making this little change, it was kind of preventing a misalignment between the coordinate reference and then the actual visual tokens that they should kind of map to. And then the fine-tuning recipe. So the original implementation of GUI actor, it had implementation for they're Microsoft, dude. They got high-end GPUs. They got distributed training. It's no big deal for them. But I'm just one dude working on an A100 on Colab, right? So I needed to simplify this a lot, because a lot of that code was just not necessary for me, and I'm sure perhaps many of you in the audience. So I had to strip away a lot of the distributed training framework and all the stuff with the deep speed and accelerate and all that, which then meant I had to build in some kind of memory optimization strategies. So one of them was just kind of reducing the maximum sequence length and the pixel count, that so that they could still kind of accommodate most GUI interactions, but then just reduce the memory requirements. I increased gradient accumulation to 16 steps so that we could simulate a larger batch size. Because I was just doing batch size of one, because otherwise I was running out of GPU memory even on the A100 on Colab. So just did gradient accumulation over 16 steps. And then I built in something a little bit beyond what the original code base had, and this was just kind of selective parameter unfreezing, right? The original code base was either freeze everything for fine tuning the entire model or unfreeze everything, right? Which makes sense if you're training from scratch, but we're not training from scratch because we're going to take a existing GUI actor model and then further fine tune that on our data set. So that means we can kind of pick and choose what we want to freeze and unfreeze. I created something like called a single app mode, which is, if you are fine tuning this on just to be able to use one app, in this case, which we are, I wanted to use 51, then will be will unfreeze layers just specific for that. So end up unfreezing some vision and language components to hopefully give deeper kind of specialization. I don't know yet because I haven't haven't tested the model, but the code runs and the code works. The model trains. I just don't know if my choices were good or not. I didn't have enough time to run any ablations because again, I just did all this in like 3 days. There's also different learning rate strategies. We'll talk about all this in a second. But yeah, so these are some of the things that I had to do to get to where I needed to be. And so just pulling this up, right? So here's the code base for what I've created. If you run this on the 51 data set that we've been working on, it should run end to end with no problem. But just kind of comparing and contrast, you can see like I've been doing a lot of work compared to the original GUI actor. But you can see the original GUI actor, like all the stuff they had. I just kind of stripped down a lot of it because I didn't need it. The core of what we're doing is all in here. Not sure why it's not clicking. All right, anyways, so you can check that out there. But everything is also in this notebook that I am going to share a link with right now. So I'll give you this notebook. I don't know why I can't click on anything. This is weird. Okay, there you go. So I'll give you the link to this, and then you can find this as well. All right. So just to kind of talk through this formatting of the data, right? So we load our data set from the Hugging Face Hub. This is the one with just 739 samples. Of course, you should generate more synthetic samples, get up to 30, 40, 50,000 samples if you could, and then fine tune on that because 739 samples is not enough really for a model to, to learn much of anything. But I digress here. So initially, this is what a 51 label looks like, right? So all I'm doing here is I'm taking the first sample from the data set, I'm accessing the key points field, and then I'm looking at all the key points within the key points field and grabbing the first one, right? So this is what a 51 annotation looks like, right? We got the label, the point, and the task description, as well as some element information, right? But I need to format this into something for a vision language model. So I needed to create a conversation, right? And so what I did was here, I created a system message for key points and a system message for bounding boxes. And then I added to each annotation a message payload. And you could read through all this here, but just constructing a standard message payload. If you've worked with vision language models, this should look familiar to you. But the end result now is that I have this, right? So I went from having all this and just easily parsed it here, right? It's just easy to do it in 51. Like if you were to export this to JSON, then having to, it's just a headache, right? So you see here 51, pretty easy, straightforward to do, but we construct a message payload, right? Once I do this, of course, we need to create a training and testing split. So that's what I'm doing here. So I've got train and validation. And at this point, I'm still working with just a 51 data set, right? So I need to get to a PyTorch data set because that's what a model is going to train with. So to get to a PyTorch data set from 51 data set, we can import this get item class and then create a subclass from that and create a get a class that just gets data, right? I'm saying that I need to have these fields, and this is how I need to grab the message payloads, right? Like if I have key points, then get the key point message payload. If I got detections, do the same thing, right? And at this point, what we have here is each element of this is now returns a PyTorch data set, right? Each element of this PyTorch data set has, the multiple annotations, right? So I need to flatten that, right? So that each element of the PyTorch data set references one image and one annotation, right? So that's what we end up doing here, right? So one image, one annotation. This way we're not blowing up GPU memory. And so then just essentially, creating the torch data set, right? So I take the train view, I use the toTorch method of the data set, and then just pass in the instance of the data getter. And then from there, just flatten the data sets, right? So this is what I end up with now, right? So there's a ton of collation that has to happen behind the scenes. So just to call that out, I think I have it here. How we collate the data set, you could see all of it's in the dataset.py. We talk about like kind of how to reformat coordinates, right? So the original GUI actor code base was reformatting coordinates to be pi auto GUI type of outputs. So I had to rewrite the regex pattern to work with what it is that we have. We have to get the token indices. There's a ton to do with that. How do we handle multi-patch labels? So token indices here, primarily just for converting points to a visual token. And this is creating for the region, right? So binary mask for a region on the input image. And then this is just the data set collator that we had to build, right? So we load, pre-process the image, extract the coordinate information, tokenize the text, get the visual tokens and patch labels, and then batch all the samples together. So pretty just a standard PyTorch data loader, really. So that's all that we're doing here. All we're doing is we're going into each one of those, we're grabbing essentially the message payload, right? Grabbing the message payload off of each instance in our data set. And then from there, we're just doing standard stuff, right? Processing the vision info. This is what we need to do for Quen. We need to apply the chat template. Then we reformat the coordinates. Then we pass all of this to the processor. And then with that output, we're able to then extract our visual tokens and multi-patch labels and all that stuff. So a lot of custom collation that was different from what the original code base was doing, because our message formats are different. And they're different because we're teaching the model to do something different, right? I'm trying to change the behavior of the model, so I had to change the behavior of the collation, right? So that's what was happening there. And then from here, just kind of the best practices for fine-tuning the model. So you can look, there's if you look in trainer.py, so the original trainer here, this is this original Microsoft trainer, right? So original trainer here, like the super, just a lot of stuff I didn't need, right? They're using a lot of stuff from Accelerate and Deep Speed and distributed training and all that. So I stripped all that out. You'll see here that there's a lot of code here to work with Hugging Face data sets. I just removed all of that because I'm keeping it simple. Like I'd never intend on using this particular fine tuning code based on a Hugging Face dataset. I'll only use it on 51 datasets that follow my particular format, which is Kogo for GUI format. So I stripped out all that stuff because it took me nearly a day of debugging. Silent, like there are silent failures that just were like banging my head against. You guys don't understand like how worn out this had me before I realized that, oh shit, it's just this additional code uh, in here specifically. Like there's some it's yeah, there's a remove columns, right? There's remove columns, right? So this was just this right here was removing all the columns from my PyTorch dataset because it was trying to treat my PyTorch dataset like a Hugging Face dataset. Uh, and it was just a nightmare. So I took that out, took out everything that had to do with processing Hugging Face datasets, and made it just strictly for working with 51 datasets. And so the original code base uses the AccuViz trainer, which is a different repository. And there's not a whole lot of change that I do to the original trainer. So that we're just a standard trainer. So we're not using SFT trainer, just the Hugging Face Transformers trainer. So there's that. And then the training recipe, I kind of diverged from the training recipe a lot. So you can see here the original training code is on this level, and it's here. So remember, these guys are training the model from like essentially from scratch. They're taking Qwen 2.5 VL and training that whole thing to become GUI actor. But I'm taking GUI actor and then further fine tuning it for my use case. So there's other things that I could do, right? I don't need to use their exact recipe, and so I just added in a few things, specifically, this ability to do what I call single app mode, right? And so also selective layer wise, freezing, unfreezing, you can experiment with that. I used a higher learning rate. I used more of a warm up, kept the same cosine decay. I used weight decay. They didn't use weight decay. I used one training batch size because that's all I have. And then, all this stuff. I end up using gradient accumulation of 16. Just use one worker because it says 4, but I ended up just using one because I was running out of GPU memory. You could train it more if you want. I just ended up training this particular instance for one epoch. You can see here, we train for one epoch. Looks like we trained successfully. Looks like I got the model pushed to Hugging Face. I haven't integrated yet, but I will get it integrated. I'll have it in the GitHub repo. I'm probably going to just run this on more data. But, we train a significant amount of the parameters, right? We train about 1 billion parameters. And yeah, that is it.